Continue our story with Cartesian tree. Today I want to implement two functions. The first function is the merge of the Cartesian trees, and the second function is split. So in the previous video we do three functions which construct the Cartesian tree to us. And now start the merge. So let's start with tab signature. To merge, how merge works? Okay, we need to construct two Cartesian tree, and how we represent them? They represent our Cartesian tree, this binary tree type, which is defined like this. And the Cartesian tree is a binary tree, binary search tree of these pairs, and also this is a heap. So they need to merge. We take one tree, they take second tree, and they produce a third tree. So as a result, they have the tree. Okay. And let's define some our arguments of our function. So we have some Cartesian tree 1 and Cartesian tree 2, and here I need to provide the definition, and this is our merge function. Okay, note that the trees CT1 and CT2 Cartesian trees must obey some constraint, and this constraint it is that CT1, every element in CT1, if we choose the x element of this CT1, must be less than every x element of CT2. Okay, so every x here must be less than every x here. And in this way we can merge these two trees and create a new Cartesian tree. How can we implement the merge? So if I take the roots from this tree and the root y and this tree and root y from this tree. Okay, because this is a binary heap trees, the maximum y values is at the root of these trees. And what will be the value of our root y value of our result tree? Obviously, this is the maximum value of one of the roots of these trees. So we need to take the maximum of these y's, and this will be the root value of our result tree. So of course we need to access somehow the name the roots, so, and we can use n-pattern matching here. We can n-pattern match our tree and its pair. It has, for example, x and y root, and it has some left one subtree and right one subtree, and same we can say same for the second tree. It has some let's mark it x1 and y1, and here x2 and y2, and left 2 and right 2 subtrees. Okay. The merge, we want to merge them, and to do this we need to do some checking of the y's. So if our y2 is greater than y1, this is the one case, and the second case, if the symmetric case, if our y1 is greater than y2. Okay. And we have no case then the y1 is equal to y2, because as I said in the previous video, we assume that our y is unique and axis is also unique. Okay. And here, if our y2 is greater than y1, we can define our resulted tree. We can say that it starts with a node. It's defined as a node, as some root node, and of course, this root node must be equal to the pair xy x2 y2. Because y2 is the greater, and the greatest elements must be in the top of our binary heap. Okay, and of course this tree must have the some left and right subtrees. We need to define them somehow. Otherwise, they also build the tree, but x1 and y1. Okay, here we have the greater case. I will mark it like this: left greater and right greater, in the greater case. Okay, let's mark it as case 1, for example. Case 1 left tree and case 1 right tree. And here we have case 2 left tree and case 2 right tree. And now let's define our case trees. So we have case 1 left tree, we need to define it, and case 1 right tree, we also need to define it. And the same thing they need to do for our C1 and C2 case. Sorry, case 2 left tree and case 2 right tree. Okay. So in the case then our y2 is greater than 1y, we can take so as I said, we take the this root and make it a root of our result tree. C1L and C1 right. So this tree have two subtrees, left and right. We can take the right tree of this tree and make it in this case the right tree, the new right tree. So this is R2. Okay, and we can take the whole this tree, all this tree, and left subtree, and recursively merge them. So we define it as a merge of CT1 and L2. Okay. Now we mean that we find the parent to every of these subtrees, of these and to this. Okay, and the done in this case. Otherwise, if our y1 is greater than y2, we need to define new left tree and new right tree. Okay, this means that this is our root, and we can take I think the left one tree and make it the new left subtree. And to make a new right subtree, they need to merge R1 with the whole tree CT2. Okay. So in the Visual Studio Code tells me that I need to add ordering here for my A and B, and it is right. I need to do this because I'm do comparing. Let's do this. So, and I think we done our merge. Note that these trees have need to obey this constraint that every x here actually here is less than every x here, so they expect this on input. And also here then they do this merging, the every x here is less than every x here. Okay, and now I think we can try to compile this and check this. But at first, of course, I need to prepare my trees which I want to merge. And to do this, I have this build function which we implemented in the previous video. If you don't see it, please see it. So we have this somehow this data. I think I want to create my one more data. Let's name it D1. I think 10 nodes will be enough for D1, and we also create D2 with also 10 nodes. Okay, and I think I also need to build 2 trees for D1 and D2. This will be tree 1 for this data, and T2 for first data, tree 1, and tree 2, T2 for second data. So I think of course this will be a IO context, and this is IO context, and they need to lift our merge function to this context. Of course they can do this, I think. So let's run our gesh CI. Let's load our file. As you can see, it's loaded. Okay. Now let's I think we need to print our trees, and we can use this expression to do this for our T1 and T2. Join. So we have this T1 and we have this T2. Now, what is the type of our T1? Let's look. Actually, it's shown here. But we can also see this inside our gesh CI. So we have this our battery inside IO context. Let's look how we can. So we have lift A2 function. I need to import it. So I think yes, we can use lift m2 function. As you can see, we can use merge for this magnetic function. Okay, we can provide the merge and t1 and t2 as the arguments. And let's look, we have this, so we can run this, and actually they have this merge tree, but as you can see they have the exceptions. And the exception of course happens because I don't define the base cases for our merge. I forget this, and the base case, then our trees are empty. And let's define it. What if we want to merge two empty trees? Obviously the result here is empty tree. And also when we have one empty and one not, we can define it as one which is not empty. Okay, this is very obvious, I think. Yes. Now let's try to reload and lift our merge function into, and as you can see they have the result. I think I can print it. Of course I need, I think, also join here to remove some IO extra layer, and we can see our merge tree. So let's look. Okay, I think there is some errors because why I have these two here. This is strange. Actually, this is not very strange because I do the error, then I do the preparation of my data. So as I said, they need to this constraint. We need to obey this constraint. But what happens here? I create some list from 1 to, actually this will be something like 10, maybe less. And this, so I not guarantee this case here because we have this axis here and axis here, and they actually this axis of d2 is not greater than d1. Okay, this means that I need to define, I think I need to define some maximum x of d1. Let's define it as 10 and use it to create this interval from 1 to mx. And here I will use mx plus 1 to I think, and let's also use mx here. I think like this. So we try to generate the first d1 in the length of mx. And I think we can reduce a little bit numbers here. It will be more readable. Okay, I think something like this. Now our d1 and d2 will obey this constraint. Actually, of course, I can check it inside my merge function. But I don't want to do this in the simplicity. In the case of simplicity, of course, we need to, for good, they need to implement this validation, but I will skip it. Okay. So let's save, let's reload, let's check our D1 and D2. As you can see, the maximum here is less than minimum here. So this interval is not intersected, and they go by increasing their x's. And now let's join our trees. Sorry, merge our trees. Okay. And what happened? You can see that I think this is the valid Cartesian tree, and they actually joined. So I think all holds here. Yes, all holds. And let's look at our initial, the T1 and T2, I think. T1, we can print our T1. And we can print our T2. Okay. And let's look at our merging result again. So, as you can see, these trees merged. Okay. Now I think we can go to the next function, and the next function is split. And let's start the type signature for this function, split function. So what we have at start, we have the binary tree, actually Cartesian tree, with our A's and B's inside, pairs, and we have some element by which we want to do the split. So this is the X element, and it has the type of A, and as a result we have the two trees. So actually this is the pair. Where is these two trees? Okay, and we can name our initial tree as T and split X as a 6. So, and let's define start the empty case. What if they have empty tree and they want to split it, but no matter what that value? In this case, they can say that they need to produce two empty trees. Okay. So, how we implement it? Of course, they need to n-pattern match the tree here. So, we have some node here, and it has some x in the root, and it has some left and right subtree. And I think we need some guards. So what we do here, we compare our x with our split x. So what if our x is less than our split x? We can be in this case, or we can sorry, or we can be in this case, then our x is greater than sx. And we need to provide definitions. So if our x, our root, is less than sx, when we can say that all the left subtree inside our interval below sx, less than sx, all the elements from the left, because we have binary search tree. But also there is possibility that some part of the right subtree goes into the has the elements which are less than our sx, and also some part can be greater than sx. And they need to take this, and how we can construct our final solution. They can take this left branch in this case. In this case, they can take this left branch and some part of the right branch and merge it and construct our result. But how can they get the part of this right subtree which have the elements which are less than our split x? Of course, we can define this part again with our definition, with our split function. We just can take the split by 6 the right tree and take the left part from it. Okay, so as I said, so we define here our pair of the result, and what is from the left? Of course, from the left is our node x itself, our left subtree, and the part of this subtree. We can say that we take the LT of the right subtree. Okay. And how we define the part which the Cartesian tree which have the greater elements than sx. We define it as greater elements of the right part of the tree. Okay, this is our pair and this is our final definition. Okay, but of course I need to define here my left right and less right and greater right. Okay, how we define it? As I said, we can run, I think, our split again for our right subtree with our sx again. And this give to us the pair which I can here do and pattern matching. And pattern matching like this. And this can be used here in this definition. But what we can say in this case? In this case, if our x is greater than our split x, this means that we can define also here some node. But of course, This x is go to the second element of our pair, because we need to provide the second element that read the greater x's. So we need some definition for left and some for right. So on the right we have this x, and these three have right subtree and left subtree, and if the x is greater than sx, then all the right subtree, I think, is greater than sx. So we skip at a moment our left tree, and we defined our right tree as it is. But here we have also left tree. And in this left tree we have possibly have some elements is greater than a 6 and some which are less than a 6. And we need to define, of course, we need to somehow extract the element which are greater from the left. And as a second element, we take the elements which are lesser than from the left. And of course, the divide it exactly the same way. We can extract this information via our recursive definition, but here we split our left subtree by this S6. Okay. Okay, we have some conflicts here with naming, and I think better to rename this a little bit. I will name it as SPLT. Yes. Split. And let's add ordering. Ordering. Okay. Oops, I have problem here because my X is a pair and I need to better match this pair. And I think like this. X and Y. And here we have X and Y. And here we have X and Y. Okay. So I hope I don't do any errors. We can try to split our tree. So let's reload. All is done. And let's print some to T1, for example. Print T1. So we have these three. this tree. It has axes from 1 to 10, and what if I want to split them by half? So I will provide. So let's look at my D1. It's inside IO. So let's split. So I think I need to use actually it is better to I think it is better to not think about the lifting here. Let's just generate some tree in an implicit way without any randomness. D. I have D. Let's define this. Let's take these D's and use these underscore here. And let's check it with this. So I want to split. It's this and go here. So I want to split these. I need to build it first, my tree. I have built function for this. I will build it like this. And I want to split it, for example, by 3. Okay. Exception. I think this exception is handled because I didn't catch the equality case. So I will add this equality here and split it into 2 trees. So now, if I take the first of this tree and print it, we have this tree. If I take the second of this tree and print it, I have this tree. And it looks like it's correct splitting. Okay. Okay, let's write some function which will do for us the generation of the random tree and do some splitting. So I will call this function SPL, and I want to define this in monadic context. Okay, what we have at first? At first we have we can take this D1 list of this D1, we can extract data from it. After this, we can use this data to build a tree. Okay, I built this tree, and now I think I can print it. I can print it. after this, what I need to do with this? Also, I want to split this tree. I want to split this tree. And I want to split it, for example, in the middle. Okay, I can take 5. Or I can take this mx and divide it by 2, I think. Mx divided by 2. Okay. This will give me a pair. Okay, and what I can do with this pair? The pair of trees. So I think a spell there, and I can use let here to better match these trees, T1 and T2, and then I think I can print T1 and print T2. Okay, let's try to recompile and run SPL. Okay, I need print TT. Use print TT. Reload SPL, and we can see our split. And let's also print the value by which we do the split. In this way. Okay, we split by 5, as you can see. So if I split by 5, the first tree with the axis less than 5, we can see here we have 1, 3, and 4. And the second tree with the values is equal or greater than 5, you can see here. And this is the correct Cartesian trees. Okay. I think this is correct results. Time complexity of this function is log n. It is we can very easily see this because on every step we go some level down, and we can't do more steps than the height of the tree, and as we know, the height of the Cartesian tree is have the logarithmic height. And same way in the merge function, it takes log n time, because here we also move now here we better match the first or the second tree, and chose one of the vertices from the left or the right trees, and we chose it exactly once. So here the number of steps can exceed the height of one of these trees, and that's why it is log n of the maximum tree, I think. That's all for today. Thanks for watching. Push like, push subscribe button. If you find any errors, please write comments, and write comments anyway. Thank you. And the next video, I think we going to implement the we can implement the insertion, the deletion function into the Cartesian tree using these two functions.